Hey everyone, good morning. I'm Megan Kacholia. I'm an engineering VP at Google in the Google Research Org. So some of the teams that are in my group include Tensorflow and other related Immel infrastructure teams, as well as the Google Brain Research team, and some different teams that also work directly with our Google products, trying to help bring innovative research back to our products. At Google, AI is changing the way technology is making an impact, from improving the search engine you use every day to helping you translate words and connect more easily with the world. AI is not only helping us create more useful products, but it's also emerging as a way to help us solve real-world problems. So you can see some different examples, different images posted here, and there were a lot of things covered in the previous talk as well. All of this is happening because of powerful new models and algorithms that are being developed. These models can detect certain types of images and video content. They can provide recommendations and help us understand language. There's a lot of different advances and things that have happened in the last few years, and sometimes faster and more accurately than individual humans can. It's really impressive just to think about some of the image recognition that can happen, some of the speech recognition, the different types of translations, things like that, that are approaching or exceeding sometimes human accuracy. But why is this really happening? So I want to focus on three big advances that we've seen kind of internally at Google and that have been represented externally as well, that we really think have changed things. So first is diverse data sets. So you can see here one of the open image data sets. It's a collection of over 9 million images that we actually helped collect and then label and open source. But diverse data sets in a wide range of disciplines have become fuel for AI at Google. Whether it's an AI system to help get rid of spam, getting rid of the hundreds of millions of spam messages in Gmail, it's a lot of spam and it's always growing, or serving relevant and up-to-date content through Google News. Data is the foundation for our AI applications and in different projects. There's also a lot of other things to think about when we're talking about data that I'm not going to dive deep into in this particular talk, but I do want to mention that data privacy, data security, these are really big things that we need to be thinking about as we're exploring AI as well, and as we're exploring how we're putting different types of data into models, and then how is that data potentially accessed. These are things we think about quite a bit internally at Google. Like I said, I'm not going to focus on that today, but I do want to call out that whenever we start talking about data, we have to think about some of those pieces as well. So I mentioned diverse data sets as one of those first three big things, right? We're just seeing a lot more data that's available and a lot more data that's available externally, that's been open source, that's available to anyone in the community. One of the second things is that we're seeing advances in Immel techniques. There's some specific examples here looking at things in language understanding. So for instance, we're constantly making major strides in this space. And again, this is something that we're seeing in our research groups. This is something you're seeing in research groups across the industry. It's not a Google-specific thing, but this is just an interesting example to call out. So a few years ago, the state of the art in language understanding was recurrent neural networks. And then they worked well for modeling sentences, but they struggled to make abstract associations. In 2017, we released transformers. And transformers are neural networks that process words in parallel, right? So an advancement from going from recurrent neural networks to this new way of doing things. On the left, you can see how transformers compare against recurrent neural nets for English to French translation quality. And we see improvements there. In 2018, we used transformers as a foundation for bidirectional encoder representations from transformers, or BERT for short. I think the shorter name is so much more fun to say than having to say the much longer one. But you can see there just kind of an example of what BERT would look like. But I've been really impressed, especially by BERT, even just looking at Google internally, how quickly this advancement was made, and then we've seen adoption. Right, seeing adoption across products, seeing so much enthusiasm for it externally. I think that's another thing to keep in mind as we're thinking about advances in Immel techniques. Just the speed at which some of these things are being picked up, the speed at which we see them being proliferating across different research disciplines, and then getting into different types of products and getting to real-world users. I've just been kind of blown away at how quickly some of these things have been moving. And then in 2019, there was some collaboration that we did with CMU, with Carnegie Mellon University, and that is what came up with XLNet. And XLNet is the most advanced language understanding model yet that we've seen. It's outperformed BERT on 20 language understanding tasks, but again, the XL helps you understand that it really is really, really large. This is a very giant model. So when we see those first two things, thinking about data, right? We're seeing these large amounts of data available. And then we think about models themselves that are getting much more bigger, much more complicated, and in order to do interesting things, to be able to solve some of these complicated tasks like language understanding. How then can we actually solve those things, run those models, if we don't have lots of compute? I really think having more availability of compute a few years back, really, when some of the deep learning started to really pick up again, compute was one of the things that helped open the door. So we could try brute forcing a lot more things and really see what can we do with deep learning. And honestly, it's just exploded from there. Compute is one of the huge things that people are exploring, figuring out how do we get more computational power? How do we make it more accessible? So again, just emphasizing, data sets need lots of compute, right? And there's lots of different types of data. So lots of different types of whether it's data points, whether it's labeled data, user-generated content. When you start thinking just about videos and just how huge those might be, just data size, and then wanting to process lots of them, again, big numbers that we're talking about here. And then again, the models. Increases in model accuracy require much more compute. I don't think that's a shocking statement. But when you start looking at some of the numbers and start thinking about how many different types of resources, how much compute power you have to put behind something to get some of these numbers, the numbers sometimes are a bit astonishing, honestly. So this leads me to the third big advancement in powering Immel at Google. And that's accelerators, really, what we call TPUs, tensor processing units. So Google and many other companies are looking at doing things like this as well, where we're designing custom in-house accelerators. So TPUs are Google's custom in-house accelerators. There was TPU v1, which we launched internally in 2015, and this was an inference-only processor. In 2017, we launched TPU v2, and this was also made accessible on cloud. And this was for training as well as inference, so working across the board. One of the most interesting things about these accelerators is that they can be hooked up together, right, in what we call a pod configuration. So this is just an image of what a v2 pod would look like. And again, access to these types of pods is also available through cloud, through Google's cloud. And then there's Cloud TPU v3, the next version. The internal names are a lot more fun than the external names, but we have to go by the nice numbers for talking about the ones released on cloud. And then looking at the pod configuration here. The number of cables I just find quite astonishing. Just the amount of machines, the amount of trays and chips that are actually wired together to build these supercomputers. So just kind of taking a look back, just the rapid progress. And like I said, Google is not the only one that's looking at doing these types of things. This is just specifically talking about some of the things that we're focusing on internally. So looking at the numbers across TPU v1, going to v2 and v3. So we're talking about 92 teraops all the way to 420 teraflops. And that's when we're just talking about the kind of like the chips themselves. Then looking at what it means when actually you're talking about pods. So 11.5 petaflops all the way to more than 100 petaflops. We have liquid-cooled data centers for the v3 pods. So again, advancements in compute are something that is very, very important just to help unlock some of the different things that we're trying to understand and trying to do in machine learning. And I think it's great when we can do it in a way that we can also make things accessible externally. So in this case, via cloud, as well as available just to internal Google use cases. I don't know what just happened. That's all right. So when it comes to TPUs, performance goes hand in hand with scale. There's actually a chart which is like flashing, I guess, to add some emphasis, just to show how you can compare usage for TPUs versus GPUs. I'm going to keep going, and we'll see if the rest of my slides flash or not. We'll go to the next one. OK, we're back. So not only is just the amount of raw compute important, but you have to actually be able to scale, right? What does it matter if you have 1 versus 100 and you can only actually scale up to using 10 easily? Now, if you've done different types of software engineering across any sort of task where you're dealing with large data, whether it's Immel or not, you know that scaling is tricky. Right? You scale from like your 1x to your 10x, okay, you figure it out. You try and go from 10x to 100x, you need different tricks, right? You start figuring out that different things become the bottleneck. As soon as you fix one bottleneck, you uncover the next bottleneck. That's the nature of software engineering. We've done a lot of exploration on this, just looking at, specifically with TensorFlow as the framework that we use internally, but other frameworks as well, which will be talked about, I think, in a talk tomorrow, just about Immel perf, looking at how we can do performance comparisons across the industry. But this just gives you an idea of how things scale, even across a pod scale. Because again, what's the point of having so much compute, having things like this available? The numbers are great, but the devil's in the details. You actually have to be able to use it. So showing that you can get scaling across something this large, I think is really critical. And just something that I wanted to call out here, that we are figuring out how do we use these things at scale and actually get the most out of them. But TPUs aren't just for internal use cases, like I mentioned. Again, just calling out some of the partners that we've actually worked with externally to figure out how to help them on their different types of ML workloads and figuring out how they can do things like just different types of modeling, again, large amounts of data, and how they can harness the power of large compute, which in our case is harnessing the power of TPUs. So some examples call out here around eBay using TPUs to improve their image classifiers, different things in the pharmaceutical space, Recursion Pharmaceuticals, just basically being able to train and do things much more quickly. Again, that's something else that compute power gives to you. The more compute you have, then the hope is that you cut down your iteration time in terms of experiments, right? If you're able to now run an experiment in a day instead of a week, then you can have much better feedback loops and hopefully try out more avenues of experimentation as well. So it's not just about the actual raw numbers in terms of like, yes, we cut down training time from 7 days to 1 day. There's the add-on effects that you get from being able to do something like that, especially when you have lots of folks who are trying to work together to then figure out and try different types of experiments and try different things. The time you gain, there's just so many second-order effects that you get from that. So again, all three of these are advances that are changing how we at Google are trying to solve challenging and real-world problems, really. To me, actually, that's the most exciting piece, is seeing the real-world use cases and seeing the different types of examples when things that either we're working on internally or that we're able to think about and do, and then release it to the external world and see how it's able to be used and actually impact things. Those are some of my favorite things, honestly. And in order to tie together the data, the modeling improvements, and make use of the large compute, internally at Google, we're making use of TensorFlow as our ML framework. TensorFlow is a platform that's powering this machine learning revolution at Google, and it's also something that we've open sourced. It's a platform researchers use to push the state of the art in deep learning, whether it's for different product launches. It's the platform that our production teams use to figure out then how to get some of these advances out to billions of users that we have. And I want to share a few examples of how researchers are pushing the state of ML with TensorFlow. So just looking here at kind of a ranking example. So learning to rank techniques, we use this in Google Search and in different types of product recommendations. And it's applied to data sets that are typically very, very large. Again, that large data is something that we deal a lot with for whatever it's worth. This is where the scalability of TensorFlow is an advantage. Having a scalable library like TF ranking, which is what it's specifically talked about here, it provides a unified framework that includes a suite of state-of-the-art learning to rank algorithms. Again, I've talked a little bit about just language recognition and just things in the speech space earlier. But another area of research, this is an area of research that we're really passionate about. Understanding human speech can be very difficult. And we want to have high-quality automatic speech recognition systems. And again, those types of systems, in order to do well, they require large amounts of data. But there are many languages that actually don't have large amounts of data available, right? So sure, you can curate data. Even then, it'll take a long time to get large amounts that you typically expect for these types of models to work well. So we developed an end-to-end system trained as a single model, and that allows for real-time multilingual speech recognition. again, figuring out how you can take advantage of big data for one type of language and have that improve other languages so that, again, the whole thing actually gets better is something that we've been really interested in doing and trying to figure out how we can do more of, not just in the language space, but other places as well, where you have different amounts of data density across the space. This is actually one of my favorites, Project Euphonia. So this helps train customized state-of-the-art speech recognition models for people with a variety of speech impairments. One of the interesting examples that was talked about in the blog post for this is for folks with ALS, which is also referred to as Lou Gehrig's disease. And so one of the early symptoms a lot of times with ALS that a large fraction of patients see is speech impairment, right? So it's just harder for them to speak, harder for them to form certain words or just certain sounds. And most common speech recognition systems then won't understand them, right? So if you're used to talking to your phone, right, or trying to use some of those other systems where you do a verbal communication with some sort of device, they'll have a much harder time understanding you now, just because the speech impairment and just things like that are coming into play. And so we partnered closely with some different foundations, specifically around ALS, to figure out how can we help. Right? How can we then take a speech recognition system and then put some special training on top of it so that it can understand these types of impaired speech? Again, you'll see these type of examples are the ones that get me the most excited. It's really cool from a technology perspective, but I think it's great that we're actually finding use cases that help people. And it's really nice when we can see some of the awesome research then feed into things like this. So TensorFlow impacts every part of our operations at Google. There are things we've done in order to help understand cooling for our data centers using machine learning to help there. Global localization in Google Maps is a new feature that was launched with TensorFlow under the covers. The Google Pixel makes use of types of TensorFlow models. So here, figuring out how to do a better job with portrait mode on one of the newer Pixel phones. And again, this is all part of the strategy of Google of being AI first. And most of our products are powered by Immel in some place under the covers. But TensorFlow is not just an internal infrastructure, like I mentioned. This has been open sourced for many years now. There's a large community around it. And honestly, I think the community is what helps make these external ML frameworks more powerful. Right? We internally, at whatever, it doesn't matter what company it's from, you'll have some sort of bias. You always will, right? Based on the things that you see around you and the types of data or the types of problems you're exposed to. And having a community that can then contribute back, can use your framework and then actually take ownership of parts of it, I really think that's one of the things that has made TensorFlow amazing, just seeing the huge community contributions. And again, TensorFlow, as we designed it, the whole idea is that there's a spectrum, a large spectrum of users that can get what they need out of it. So from researchers who are pushing the state of the art in machine learning, from data scientists who are coming up with innovative solutions to industry problems, and developers who are trying to figure out how to write intelligent applications to help their end users. And there's lots of places in between, right? It's not that you have to be strictly in one bucket or the other. You'll overlap, you'll move back and forth. And I think that's one of the things that makes TensorFlow so powerful, is that there are things then to help you kind of go through those transitions and be able to solve the problems regardless of which bucket you fit into at the given time. I have a video, which is always a scary thing to do. Here we go.
There's more extreme rainfall, heavy flooding, forest fires. There isn't really a signature done. Being able to predict these extreme events more accurately is kind of the big challenge that we're facing right now. There's 100 terabytes of climate data every day from satellites, from observations, from models. So climate data is a big data problem. We need things that are fast, that can sift through all of that data rapidly and accurately. And deep learning is almost perfectly poised for problems in climate science.
A lot of NERSC users are using TensorFlow. It's one of the more popular frameworks. We use TensorFlow to iterate quickly over different models, different layer parameters. For this particular climate project, to create the deep learning model, we started from segmentation models which have proven to be successful, for example, our satellite imagery segmentation tasks. And then we used TensorFlow to enhance the models until we found like a set of models which perform well enough for this specific task. But for the volume of the data, complexity of the data, the network required 14 teraflops. So if you want to do this on your workstation, it would take like months to train.
To really tackle these problems requires the largest computational resources that are available on the planet. So systems like the Summit supercomputer. It's 2 tennis courts in total size. I mean, this thing is state-of-the-art. It's 1 million times faster than your common laptop. 3.3 exaflops. Just imagine what you do at your workstation, but now imagine having 27,000 times that power. We can do that now.
We were surprised how good it actually scales. 1,000 nodes and 2,000 nodes, 5,000 nodes.
This was the first time anybody's ever run an AI application at this scale. Instead of having the climate scientists figure out how to write high-tune code, they could express things in a very natural way in Python in TensorFlow and get all the high-performance code that most HPC people are used to within TensorFlow.
We're now entering the space where AI can actually contribute to the predictions of these extreme weather events.
When you combine traditional HPC with AI, you can tackle things we never thought that we could tackle. Fusion reactor research, understanding diseases like Alzheimer's, cancer, right? That's incredible.
We've shown that with a high productivity framework such as TensorFlow, you can get to massive scale and you can get awesome performance and accomplish your goals.
Genetics, neuroscience, cosmology, high energy physics. That's immensely exciting for me.
I'm so excited the video worked, you just never know. So one of the things, there are 2 things actually that I love about that example. One, just kind of being repetitive. I love the real world examples. 2, that example was not just me showing all of these things that Google was doing. There were lots of different companies that had to collaborate and work together in order to actually make that example happen. And I think that's something we should all be thinking about and pushing for, right? Sure, there are some things where it's, competitive, we work against each other, but there are lots of places where collaborations like this, it's amazing just to see the different things that it can be done. For this specific example, they won the Gordon Bell Prize for applying deep learning to study the effects of extreme weather platforms and impact on communities using high-performance computing. So again, there's great things that we can do, and this is a great example of it. I want to briefly walk through just some interesting things happening with TensorFlow, and then kind of close out my talk here. But again, TensorFlow 2.1, so that's the newest release that we have available. Pardon me. We recently released TensorFlow 2.1. It continues the momentum of 2.0 with major improvements and some bug fixes. This chart just kind of showing how TensorFlow, how we conceptually think about it in terms of how things are set up. You might be familiar with this type of diagram, but I want to emphasize how 2.1 makes the workflow even easier and more intuitive to use. One of the big things is just kind of the high-level APIs, so thinking about how Keras can fit in tightly with TensorFlow. There's actually going to be a talk on Keras, I believe tomorrow. I think Francois from the team is also giving a talk, so I'm not going to go into a lot of details here because he'll share more. But it's just important to call this out as our high-level API and something that we're continuing to focus on. When you need a bit more control to kind of dive down, debug, go through things step by step, that's where eager execution is really important. It's familiar just because of the Pythonic function execution. It makes for easy debugging, and again, makes for that easy step-by-step control flow. There's always different add-ons and extensions. There are more things called out here that are compatible with 2.1. I think there's some interesting new libraries in the ecosystem as well. Neural structure learning. I think the fairness indicators is a really interesting one as well. It's an add-on that enables regular computation and visualization for fairness metrics. Again, this is something where, as Google, I'm really excited to see that when we're figuring out how these different things that are important, whether it's related to fairness, privacy, things along those lines, how can we open source it and make sure the community has access to it as well? And this is one I'm really excited just to see that we've open sourced recently. Tensor Board is something that many users love. Really excited to be able to to do visualizations, right? What's the point of having data or kind of digging into your models? You want to be able to actually try and dig in and understand what's going on, do comparisons across experiment runs, and so on and so forth. We've seen a lot of excitement with Tensor Board. We see people taking screenshots, right, in order to kind of share their experiment results. And that was something that prompted us to want to do tensorboard.dev. So this is basically a hosted Tensor Board service. So that way you can take a URL, your logs, be able to upload your logs, get back a URL, so that then you can actually share that and be able to more easily share your results versus having to share like a static screenshot. So this is something that we've done in collaboration with some other teams at Google. Tensorflow Hub has been available for multiple years now. So it's a repository of ready-to-use pre-trained models by the community. I think that's, again, the community aspect of TensorFlow I think is very important. There are models available on TensorFlow Hub from Google, obviously, but also from Microsoft, from NVIDIA, from multiple other companies and just contributors as well. And there'll be more we're adding in over time. And so just thinking about here the improved experiments of TensorFlow Hub, this was something that we tried to make much better and more intuitive to use with the 2.0 release, make it easier for you to find the types of models that you're interested in. And also, again, the whole point of this is that it makes it much quicker in your iteration cycle, that you're able to use these pre-trained models, use something else so that you don't have to go through all of the kind of deep work yourself. And like I mentioned already, there's models by the community that are then contributed back to TensorFlow Hub. And I think this is a great way for us to just be sharing more things and building on all the momentum that Immel has across the community at large. One of the important things about TensorFlow is being able to deploy Immel everywhere. This is, again, has been something that we've always focused on. And there's been more specific things that have come up as time has gone on. So figuring out how can you take a model and then make it work on like mobile devices for TensorFlow Lite? How can you do things on JavaScript for using it in different types of environments? And of course, TensorFlow Extended for thinking about how to doing things end to end. How do you do serving? What's the point of building a model if you can't actually serve from it? And figuring out how those pieces go together regardless of what your deployment needs might look like. And again, TensorFlow 2.1 now has support for cloud TPUs, so making it easier to use cloud TPUs, especially with Keras. I want to just briefly call out as well kind of a different piece of all of this, which is AI solutions for Google Cloud. So there's a lot of different things that cloud is doing to be able to expose, that Google Cloud is doing, to be able to expose solutions to make things easier for developers. So you can see some of the different things here that are being done. Again, what I think is most interesting about this is that basically there are now APIs that you can make use of for figuring out translation, right? You can call an API and make a translation call. You can call an API and be able to do image classification. And it's really exciting to see how the research done in the research groups at Google is then exposed back to, basically back to enterprises, back to companies in ways that they can take advantage of through these different types of cloud services. So we truly believe AI should be for everyone. Like I said, I really think there's these three big pieces when you think about data and then how the models have improved and changed, and then just compute power, how having access to different types of compute power, more compute power, has really moved the needle on things. And again, I think it's really exciting just to think about what we can do. I look at it thinking about it from Google scale, thinking about how we can bring these things back out to the world. But I think we should just all strive, do more as a community together, and then we can do some awesome examples like was shown in that video as well. So thank you. Any questions?
Thank you, Megan. We have time for a couple of questions while Andre is setting up.
Yes. I don't know where the mic are. I think there's a question.
Hello.
Hi.
So I remember that at Google there was this vision that sooner or later the superintelligence is going to arrive, and it would be great for Google to be the hotbed for it, the origin. And there were some sentiments that the Google's stock price today is a reflection of the infinite utility times the probability of Google bringing this up. So what do you see? Like you describe here a lot of things that you're taking on a practical level, like shipping last year, this year, next year. But what are your views on the superintelligence and how that fits into the earlier talk about like its dangers and benefits?
That's a really complicated topic. I think there's a couple of different things. I I think there are a lot of amazing uses for machine learning and AI that can help supplement people, right? So I was listening to the talk earlier, even just talking about some things on the healthcare space. I really think that even in that space, how it's really helpful is able to supplement people when, let's say, you have healthcare workers and there aren't enough of them given the population, right? If you think about underdeveloped countries or things like that, or developing nations. And you can find anything on the internet, right? So you can search and find like different types of scary predictions, but at least for me personally and how I look at things with my teams is how can we augment and do things that are useful, right? And make sure that we're approaching machine learning from that aspect. How can we make sure we're holding up to the AI principles that Google has released, right? And talked about externally. This is something that it's not just an external like press thing. This is a real thing that we have to talk about and think about internally in terms of like, what are we publishing and does it make sense, right? Is this an area that we as a company want to be working in? Does it make sense? How are we thinking about this from the societal impact? So, I mean, I think that sure, there's definitely lots of ways to get things wrong, but I do feel like we're trying to find ways to do things right and look at ways to help.
Thank you, Megan. Let's thank Megan one more time. And she's here. Can you hang out at lunch and other things so that people can take questions?
I will try.
Okay. Thank you. Thanks again.
Thanks.